The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today we start on Project 4, which is, as you know, the big project. And Helen is going to do a walkthrough of the project and the code and the organization because this is a pretty big size project. It's got about 4,500 lines of code, and it's not code that is kind of like simple code. It's all content-bearing code. So I think having a bit of an orientation to it, more than we give for the other codes that you work on, which are pretty small, this will be great. So Helen, take it away.
Awesome. Hi, everyone. Can you hear me? Awesome. So today we're going to be doing the walkthrough for the final project. You can look at the code and clone it publicly here. And please remember to fill out your teams by 7 p.m. today so we can populate the list and get you your repos. And if there are any issues accessing this, just let me know or put a note on Piazza and then we can fix it. So we just had a game up of Laser Chess, but in case you missed it, and we'll go into more details about what the game actually does. So first we're going to go through the game rules. So you saw that there are these pieces. There's these triangles and there's kings. So the triangles are pawns and the kings they look like crowns, and there are two teams. There's orange and lavender, or tangerine and lavender. And each side starts out with 7 pawns and 1 king. And this is the starting position. So you can see like the kings are in the corner and they're just lined up, like in the middle. And each piece has 4 orientations. So you can see that the pawn is like right, down, up, down, left, right. And then the king is also like that. And in general, the game starts with tangerine moving first, and then the play alternates between the 2 players. Each piece moves the same, whether it's king or pawn, and each turn has 2 parts. So you saw in the demo, but you move first. You pick one of your pieces and you move first, and then at the end your king has to fire the laser. And the laser reflects off the long edge of the pawn, and it'll kill the pawn if it shoots the short edges. And one side wins when the king gets shot, or when the opposing king gets shot, whether by themselves or by your own king. And so I talked a little about moving, and at the beginning of each turn, the player to move chooses a piece to move, and you can move your king or any of your pawns. And there are 2 types of move. There's basic moves and swap moves. And basic moves are just basically shifts or rotations. So in the example, you can rotate 90, 180, or 270 degrees. So in the top row, you just rotate. This is an example of moving a pawn. So you rotate your pawn, or you can move to an empty adjacent square. So those are the bottom 2 rows, and there are 8 adjacent squares in this example. So there are 8 shifts, but there would be less than 8 if you were, for example, like at the edge of the board. And on a move, you can either shift or rotate, but you can't do both. There are also these swap moves. So if you're next to an adjacent, or if you're adjacent to an opposing piece, you can switch with them, and then you have to make another basic move after that. That is not a swap. So basically you can either, again, and it has to be with that same piece that you just swapped with. So you just either shift or rotate. Is everyone good on the rules? Just a couple more things. So there's this co-rule, which is from Go, which ensures that the game makes progress. So it makes a move illegal if it undoes the opponent's most recent move by just moving back to where you just were. So this is an example. Let's say you're tangerine, and you swapped with the purple one right next to you, and then you shifted like left and bottom. And so lavender can return by swapping back with your orange piece and shifting again. But this is actually illegal because now you just got to the original position. So you're not allowed to just keep cycling back and forth. And so a draw occurs if there have been 50 moves by each side without a pawn being zapped. The same position repeats itself by the side on move, or the 2 players agree to a draw. So just kind of like in chess, a chess clock limits the amount of time the players have to make a move, so you can't just keep competing indefinitely. When it's your move, your clock counts down. When your opponent's move, your clock stops, so it's not counting your time. And we use Fisher time control. That's a picture of Bobby Fischer, who made it up, which uses an initial time budget and a time increment. So in this example, there's FIS 60 and 0.5, which means that in the beginning, each player has 60 seconds. And you get to use the 60 seconds however you want. And when you end your move, you get 0.5 extra seconds. But those 60 and 0.5 could be anything. So that's just an example. So we'll go into an example of how you actually play this game. For a king to zap the enemy king, it risks opening itself to counterattack. So look at this example, and how can Tangerine zap the lavender pawn on f5 by moving one of his pieces? Move c4.
No, tangerine, that's lavender.
You're Tangerine in this example. Yeah, sorry. And you're trying to zap the one on f5. Yep.
You move the Tangerine piece at e2 to f1.
At e2 to f1. Wait. To f5? Oh, sorry. By zap, it means like shoot the backside. Like that would shoot the long side. Good point. Yeah, so you're trying to kill the piece on f5. Mm-hmm.
You can move c2, c3.
Yeah, exactly. So in this, you can move c2 to b1 as you just said, and then you draw the path, and you can see that you've just killed, or if you're Tangerine, you've just killed the piece at f5. Now how can Lavender counter? By counter, we mean Lavender can win the game from this position. Mm-hmm.
Is it a4 to a3?
A4 to a3. No, I don't think so. Yep.
King to b6.
Sorry, what?
King to b6.
King. Like the orange one? Oh, the lavender one. You're trying to shoot the orange king. Oh, yes, you're right. You can, actually. Yes, good. That's not the one that we had, but apparently there are two ways. Good. Yeah, so as you notice, you could also, that's another way to get that path, but you could also move one of the pawns. Cool. So, yeah, so this is just pointing out one of the subtleties of the game, which is you should watch out for just naively killing all the pieces you can, because that might open you up to the opponent. Yep.
Does the king die if you shoot it from any direction?
Yes. It can be from any direction, but the pawns only die if you shoot them from the non-long edge. Yep.
What if you shoot your own block?
Shoot by block, you mean your own pawn?
Yeah.
It'll die.
Oh.
Yeah. Yep.
Can you place people directly adjacent to yours?
Yes, but only one piece can be on each square, but you can have as many like near you. Is that your question?
Can you make it impossible to kill your person?
Like your king? Like if you barricaded it by pawns, but then the opponent can come in and swap with them, so it'll open your barricade.
Could the purple king shoot upwards?
If it wanted to.
Okay.
But then in this example, it would just shoot off the board and nothing would happen.
Yep.
Yep.
When you kill a pawn, does the laser stop at the place where the pawn died, or does it like go through the pawn?
No, you're right. It just shoots one. Good questions. Is everyone good so far?
This year, it shoots only one. Last year, it kept shooting.
Can the king shoot itself?
Yes. You should try not to, but it can, so you should be careful. Great. Okay. So moving on, we use force editor's notation, which is a representation of a chess position using a string. So this is you can see an example of the starting position, and the bottom includes the string that describes the starting position. If you look at the representation, the arrow corresponds to one of the rows, and that points to the substring that has a bubble over it. So in this row, there's one purple pawn at B3 and 2 orange ones at F3 and G3. So this is row 3. And the slashes separate the rows in the string, and the 1 represents there's an empty space, and then there's a pawn facing southeast, and then there's 3 empty spaces and 1 facing northwest, and then 1 facing southeast, and then an empty space.
So that's animated.
Oh, yeah. You can just animated. What do you mean?
Okay.
Okay. Okay. Yeah. So at the end of the string, there's also it just tells you which side's move it is. So this is the opening position, but you can use any position in this notation. And this is useful for debugging because if you, for example, you're running your bot and it crashes at some position, and you can get back to that position, you can start up the game and just go there without having to make all the moves to get there. Okay. And this is how you represent the games. So each of these is one move, and the left column is tangerine, and the right column is lavender. And in the example, you can see E6, E7 means that you moved a piece from E6 to E7. B3L, so you rotated the piece on B3 left. There's D5, E4, F5, which means that you swapped. So your original piece was on D5. You swapped with the one at E4, and now you moved that piece to F5. So the one that was at E4 is now on F5. And the opposing piece is now on D5 because you swapped. You can swap and then rotate. So instead of just having a third square, you would just have a rotation. And at the end, you can see who won. So in this one, lavender won because it's 0-1, but 1-0 would mean tangerine wins, and half and half would be a draw. So you can look at the logs for your games. Oh, yes.
Is it like a rotate right and a rotate left?
Mm-hmm.
You rotate one and then
There's a rotate up and rotate down.
Pause. Do a U-turn.
Oh,
U is-
is that what U is?
Yeah, U-turn.
Then which? Oh, okay, I see, because there's only 3 rotations. Yes, sorry. So left is 90, then right is 270, and U is 180, because you flip it. Is everyone good on the notation? So this is just how you describe the games if you wanted to look at your logs and if there's some issues. Okay, so you can test your bot with other teams in the class as well as the staff bots on the scrimmage server. And we have a reference, which is here, which is just the initial release, but we will be optimizing our bots while you are optimizing your bots, and we'll release a reference plus and maybe an even better one later, which you can play with on the scrimmage server. So I'll just do a really quick demo. So right now, since we haven't done the team formation yet, you are not able to log into this, but once you do your team formations, probably by tomorrow, you'll be able to log in. And basically, you can see the general functionality. So this update your player pulls your player from your repo, whatever's on the master branch. And then right now, there's only reference and reference plus and reference TAs. And here's a team with me and Jess. But you can, later on, we'll populate this list with everyone in the class. And then you can challenge anybody else in the class to see how you do. And you can also challenge us. So you would just pick, for example, let's say I wanted to challenge reference. And then I hit send challenge. Now you can see that there are some new matches spawned. And this is how I look at all the matches that I've played. So each time you hit send challenge, it spawns off 2 games, one where you're tangerine and one where you're lavender. And yeah, so that's how you can watch the matches on the scrimmage server. Is everyone good? Okay, so I'm gonna move on so we don't run out of time. But you can watch them later. And you can even play your own. Okay, great. And in addition to the scrimmage server, so the scrimmage server, you can only spawn off one game at a time, but you can do more, and you don't have to necessarily do it on your master branch or against opposing teams in the class. So there's something called the CLAD auto tester, which you can run by going to your Athena, and then you type in this command, you do auto test run, and then you do the time control, and you give it a number of games that you want to run, and then you give it a list of binaries. So I'll go into each of these in more detail. So the time control is just what I talked about earlier, which is if you use Fisher time control, these are some preset things. So you would type in one of the preset things. So you type in blitz to do 60 and 0.5, for example. And the number of games is just whatever you want to do. And the list of binaries, so let's say you had a reference implementation and then you made some change. So I called it Lizer chess with changes. And then you would just put those after the number of games separated by spaces, and then it would upload your binaries and play them in the CLAD auto tester. And once you submit your job, you get a link, and you follow the link in your browser, and you can view the games running. And then after the games are done, you will get like some output saying like which bot won more and how many times it won and some rankings. Yep.
How fast do they run?
How fast do they run?
Is it just like if we say blitz 60 or something, will it run in 60 seconds?
So it depends on how many other games are queued at the same time. So if a lot of people are running tests, it might take some time. But blitz is just how long the game itself will take. And it might take longer than 60 seconds because if you use less than 5 seconds in your 0.5 seconds in your move, and then you add 0.5 seconds at the end of the move, then you would increase your time. But like 60 is just the time control. Like it doesn't mean each side starts with 60 seconds, and depending on how they use it, they have more or less. Good question. Right. Well, I'll keep going, and if there's time at the end, I'll do a demo of this one too. But it basically looks the same as the scrimmage server. Like you just watch the games in the same way. Right, so now I'm going to go into the project organization, which is the organization of the directories that we handed out in this repo. So there are some directories. The first one is doc, which just includes the rules and documentation for the interface. There's the auto tester, which is the Java local auto tester. So if the cloud auto tester, like we recommend that you run tests using the cloud auto tester, but if there's some small change, or if you think that like if the queue is too long, then you can do local tests. And you can also run these like overnight. There's PGN stats, which just parses your statistics from the auto test results, like how many times you won and stuff like that. There's tests, which is how you specify tests, and I'll go into more detail about how you define those. There's player, which is what you're actually going to be optimizing. So player is the code that actually runs the bot to play the game. And the web GUI is a local web GUI where you can watch the game and play it. So in the web GUI, you can even like play it yourself as a human. So you can get a better sense of how the game works. To go into more detail, the Java local auto tester is an auto tester, and you can change your bots. You can make your changes, and then you can test your changes. And the test directory, which is parallel, holds configuration, so you can specify the number of games and the bots that you want to use and the time control and other things too. So this is an example of the configuration file that you would use to run your auto tester. So this is saying that you run on 12 CPUs, and book means that you're pointing to an opening book, which I'll talk about later. Game rounds is how many games you're going to spawn off. Title is just the title of the test that you're running. And after that, you have the player definitions. So player reference is just the binary. And invoke is the path to the binary. And then FIS is the time control. And the next one is just a second binary if you made a change and you want to test them. Oh, yeah, that's the binary. To interface with the AutoTester, LaserChess uses the Universal Chess Interface, or UCI, which is a communication protocol for automatic games, and you pass information between the AutoTester and your bot. And it allows the programmer or the AutoTester to enter moves to the game engine. So you could use UCI to start up your bot, and then you type in the moves that you want to make to see the changes in the state. And you could use this to debug to get to a state that you want to look at. We'll measure the bots using ELO ratings. So ELO is a rating system that measures relative skill level in zero-sum games. The ELO rating depends on the ELO rating of your opponents. And on the bottom, you can see an example output. So I had 3 binaries, and I ran about 100 games. And you can see that the ELO of the top one is much higher than the other ones. And so higher ELO is good. And we'll be comparing the performance. We'll be comparing the ELO of your bot against our reference and improved reference implementations. So notice that this is not, as before, just a straight measure of time. So like before in previous projects, it was if you use less time, then you would get a higher grade or better performance. In general, I'll show you a graph later that actually shows if you search to higher depth, which means that you are faster, you do improve, but it's not an exact correlation. And you can look at the nodes per second that you search in the using the UCI. And just to wrap up here, the local web GUI lets you watch a game or play one without sending it to the scrimmage server. So if you wanted to play one as a human, you would use the local web GUI, and you can run it using the commands in the README. Okay, so is everyone good so far? Now I'm going to go into more details about how you actually play the game. So first, every player or every bot needs to generate the moves, which means that once you have a position, you need to look at the moves that you can do. And to do that, you need a board representation, which is to represent what pieces are on the board and how big the board is and where the pieces are. And the reference implementation uses a 16 by 16 board to store an 8 by 8 board. So you can see that the inner square is actually the board, and the outer dark square is sentinels. So use sentinels to keep track of when you go off the board, and then the inner square is just the actual board. We store the position using this struct, so you can see the fields in the position, which are the board, and the array size is just like representing the board plus the sentinels. And there's the history of the position, which is how did we get here, and there's a key, which is a hash key for this position. There's ply, which tells you what side it is, so even means white and odd means black. There's what was the last move that was made to get to this position. There's a victim struct, which is the pieces destroyed by when you shot the laser. And there's the location of the kings. The position struct in LaserChess stores the board representation and other things that I just went through. So I talked about this move, which means just like a move that you make for one of your pieces. And I'll go into how it's represented. So right now, we already do the packing for you. So we use 28 bits. And the first 2 are the piece type. So this is so there are some number of, there's a number of moves that you can make. And the first 2 bits represents the piece type, which is empty, pawn, king, or invalid. The orientation of the piece, which is just how you rotated it. The from square, which is where your piece already started. There's the intermediate square, which is used when you do a swap. And there's a 2 square, which is the final position that your piece will end up in. So if you're not doing a swap, then the intermediate and from should be the same. But if you are doing a swap, then there's some skipping that happens. At each turn, you need to see what moves you could possibly make. And in MoveGen, which is one of the files in the handout, we generate all the moves given a position depending on whose turn it is. So depending on whose turn it is, you can make different moves. And in the reference implementation, we iterate through the entire board. And once we find a piece, we generate all the moves from that piece. You can also debug using move generation. So there's something called perfft, which is a debugging function that enumerates all moves at a certain depth. So you use perfd to make sure that if you make changes to the move generation, that you're generating the same number of moves. And if you modify the move generator, just make sure that it returns the same. Because regardless of what optimizations you do, you still should see the same moves from each position that you can possibly make. Is everyone good? Okay, so now that we talked about move generation, I'll talk about how you tell that a move is good. And for that, we use something called static evaluation. So we use static evaluation to determine which positions are better than others and which moves that we should make. And the function eval, which is in eval.c, generates a score based on a position using some heuristics. And at first, we suggest, instead of making up your own heuristics, we suggest focusing on optimizing the existing structs and evaluation heuristics before coming up with new ones. Because it's kind of hard to come up with new ones, and there's a lot of optimizations that you can make to the existing ones. So I've just grouped these into categories. So there's a few regarding the king. So there's one called K-face, which is a bonus for your king facing the enemy king. There's K-aggressive, which gives you a bonus for if your king is closer to the center of the board. And there's mobility, which counts up basically how many squares around your king are free. And you want to be able to move your king freely. And there's some regarding pawns. So there's P-central, which gives you a bonus if your pawns are in the center of the board. And there's P-between, which is you basically draw a bounding box with both kings at the corner, and then you count how many pawns are in the center of those. And then there's ones based on distance. So there's L coverage, which means laser coverage, which is basically you make all the possible moves that you can make from your position, and then you draw the laser path, and then you do some scaling to determine how well you can possibly cover the board based on your current position. So that's basically how you tell if a position is good or not, by doing these heuristics. So I'll just go through the high level of how you actually play the game using search. And so at the very highest level, there's something called game search trees, which we've implemented in search.c, but basically this is a representation of how you play the game. At the top, there's an orange square, which is the orange side, which is the opening position, and then the arrows. So the top square, and all the nodes are positions in the tree. And you use move generation that I just talked about to enumerate all the possible moves from a single position. And each edge is a move. So to get from position to position, you do moves. And you can see that circle is the position after you've made the move. And you do this tree to some depth d, and then you do static evaluation at the leaves. So this is at a really high level how game playing programs actually play the game. They enumerate all the possible moves, and then they have a position, and then they pick which one is best based on evaluation. But you can see that there's a lot of nodes. Like if you did this naively, there would be number of moves raised to d, which is a huge number, and too many to generate. So we're going to talk about how you reduce those later. There's something that you have to do on search trees, which is called quiescent search, which is if you fix your depth, and let's say you fix depth, and then you go down to the leaves, and you just captured a piece, but it's dangerous to just stop there at fixed depth, because maybe if you searched one level deeper, you would see that the opponent would capture your piece. And so if you do your search and you see that you capture a piece at the leaves, or your opponent captures the piece at the leaves, we say that's not quiet, and you keep searching the tree until there are no more captures. So that's called quiescent search, because you quiet the position. And that's implemented in Search Common. So this is a graph that I generated by doing the reference spot to different depths. And you can see that the ELO increases as you increase the search depth. So you just search the search tree, and so if you optimize your bot to make it faster, you can search deeper, which means that you'll do better. So next I'll talk about minimax search, which is a more complex version of searching that can improve the amount of nodes you have to evaluate. So at a high level, there's two players, max and min. In our example, there's orange and purple, and orange is a square and purple is a circle, and the game trees represents all moves from the current position from a given ply, which means depth. And at the leaves, like I said, you apply a static evaluation function, and max chooses the maximum score among its children, and min chooses the minimum score. So one side is trying to maximize, and one side is trying to minimize. To evaluate the search tree, I'll first talk about an algorithm called alpha beta, which is that each search from a node has a window alpha beta. And if the value of the search falls below alpha, the move is not good enough and you keep searching. And if the value falls within alpha and beta, then you increase your alpha, which is the lower bound, and you keep searching, because you know you can do at least that well. And if the value of the search falls above beta, then you generate a beta cutoff in return. Beta basically means one side is trying to maximize and one side is trying to minimize. So you would see, beta is basically saying like the opponent would never let you do that move because it'd be too good. So you don't need to keep searching there because you're not going to get there anyway. So we'll do an example. Let's say you have this tree, and if max discovered a move that min wouldn't let you do because it's too good, then max's other children don't need to be searched, which is what a beta cutoff is. So you start at the root, and then you go down to the lowest left leaf, and you see that it's 3. So you propagate 3 up, and then you can say that in this subtree you can do at least 3. And then you keep searching your children, and then you see 6. And then you say, okay, now you update your alpha value to be 6. Now you search 4, but 4 is worse than 6. So you don't have to do anything. So you first search the leftmost subtree, and then you see the best move that you could possibly make there. So you propagate 6 up to the root, and then you search your other subtrees. But now you have this value of 6 that you basically use in the other subtrees. So you look at 2, and you see that 2 is less than 6, so you propagate it up. But now you look at 9, and you see that 9 is greater than 6. So you say that this subtree would let purple do 9, which is greater than 6. And so that would be too good because orange would never let purple do that well. So you don't have to evaluate 5 anymore. So you cut off 5. Does that make sense? Okay. So basically now you apply the same thing to the rightmost subtree, and you look at 7, and you see that 7 is greater than 6. So you propagate that up, and now you're done because 7 is greater than 6, so you don't have to search the rest of the subtree. So that's how you evaluate fewer moves than the entire tree. And there's a theorem that says for a game tree with branching factor b and depth d, an alpha beta search with move search in best first order examines exactly b raised to the d over 2 plus b raised to the d over 2 minus 1 nodes apply d. So best first order means that you sorted the moves in terms of your static evaluation. The naive algorithm examines b to the d nodes, and in the example that I did, you can see how you prune. And for the same work, the search depth is doubled, and for the same depth, the work is square rooted. So this is a huge benefit over the naive evaluation. Does everyone get an alpha beta? Great. So the code is pretty short, so I'll just go through some pseudocode for it. Basically, the main point is that at line 11, one side is trying to minimize and one side is trying to maximize, but if you negate, then that's just the same as minimizing and maximizing. And you get all the possible moves that you could possibly make using gen moves, and you go through the entire move list, and then you make each of the children, and you search for the score, and then you see whether you had a beta cutoff, and then you don't need to search the subtree if you did. Okay, so that was basic alpha beta, and we actually implement a variation in alpha beta called principal variation search. And the main idea is that you assume that the first move is the best one, and you run scout search, which is also called zero window search, on the remaining moves to verify that they're worse. So in this example, you again search the leftmost subtree, and you see that the best you can do in the leftmost subtree is 3. And you evaluate the ones to the right of it using scout search, which is not a full search. You're just testing that. You're basically assuming that you can do no better than 3, and then now you're kind of like doing an initial search to see whether or not that's true. And so you see that some of them are, or the one after that is 7, and the one after that is, or the first one after that is 7, and the one after that in the other subtree is 6. So then you can prune them because those are better, because you know already in those subtrees that you can do better than 3. So you don't have to keep evaluating them. And then you don't have, yep.
How do we know the score of a subtree before we evaluate it? How can we prune something without?
So you're not actually like, so you actually had to find 7. Like 0 and 8 are there, but you haven't found them yet. Like, so you basically, if you thought about doing it serially, you would do the leftmost subtree, which has 2, 3, and 0, and then you would find 7. And then that would be a cutoff because 7 is bigger than 3. So you're not actually finding 0 and 8.
So we were just like okay with not getting 8.
Yeah, because like you wouldn't, the point is that you wouldn't get to that subtree because the opponent wouldn't let you get there because you can do better, because you can do too well, so they would just not let you go down that path. Like let's say you were purple and the opponent is orange and you want to get 7 and 8, but the opponent can also search that and see that you would get 7 and 8, so they would prefer you to do something like 2 or 3. Is that okay?
So what do you do instead?
Oh, then you don't, then you have to, like basically you're kind of, like you're not always making the best move that you could possibly do because, like if you just searched without this pruning and you just picked, let's say you wanted to make the best move, but you're, like if you don't take into account the opponent, then you're never going to get to there. So you're basically trying to find a move that the opponent would let you get to that's also good for you. Because you switch off. Oh, yes.
What are we playing as in this example?
I guess in this example, you're purple.
The score is in the
Or no, sorry, you're orange because you're cutting off. No, you're purple because you're trying to maximize what you get at the leaves.
The scores in the circles are the scores we would receive as purple.
Yes. I think. Okay. Yeah, the main point of, sorry?
Oh. We're orange. We're trying to minimize the score right now.
Yes. So orange is trying to minimize the score and purple is trying to maximize the score.
So we're cutting that off and saying we don't need to search this because we already know that there's a 7 here. So we shouldn't go down this path anyway.
Does anyone have questions? Does that make sense? Yeah, it's basically exactly as you said. So, like, there's kind of this balance between one side trying, like, both sides are just trying to make the, like, you're trying to make good moves, but you're also not trying to make the opponent make not good moves, if that makes sense. So you're not only searching for your maximum, but you're also searching to minimize the opponent. Yeah, good question. Yeah. So.
No, we're definitely orange. Because
Sorry?
So, we don't want to choose either of those orange ones. We don't want to let.
I think it's okay. I think you can move on.
Oh, okay. Yes.
This is important.
What if you and your opponent have different reward criteria? Like you guys evaluate
That's okay.
criterion differently.
It's fine. I mean, like the search, like the actual evaluation, like what number you assign to each position is not exposed to the opponent. Like the main point is that at the end of each move you pick one, and they can do with it what they want. Like that may not have been the one that they picked, but it's okay. sorry, I think you're orange in this one. Well, because the root is orange. Yes.
So I interpreted this graph as saying like you were picking between like the 3 purple choices, like you're purple and you're picking one of those, and then like you're looking at the first choice, and then like you see that the like how orange could respond is like it gives you something with s equals 3, and then you know that orange won't respond with the next 2 because it'll give you better choices. So are we orange or purple?
All right, let's start over. So I think that we are orange, and the purple is not, so remember that each edge is a move, and each node is a position, and so you're orange, and you start at the root, and now you, for example, make the move left, and purple now can make moves, whatever, 3 after that, and now you're orange again, and then you can make moves after that, and now you evaluate the position after that as a leaf. And so basically you are searching past like the second level of orange, and you are cutting off if you see that you would do better because you think that purple would never let you get to that orange node right above. Yes? Yeah, I guess that's the score that you as orange would receive. Yeah. You are, or I mean, you're not trying to give, it's not so much like you're trying to give purple 0 as you think that purple would not give you 7 and 8. Because purple would have to go down the left subtree to give you that. Okay. Yeah. Other questions? Okay, anyway, I'm going to move on with the search then, if there are no questions. All right, so.
We don't even keep 6 and 7 anyways, we just want the knowledge to separate, right? So we already have them, but we keep them, or do we get rid of them?
Basically, you're not.
Is everyone good? Can I keep going? Okay, thank you. So just going back to principal variations pruning, the main idea is that you go down the first path on the left side thinking that that's the best subtree, or thinking that's the best path, and then you're basically doing initial passes through the tree to make sure that your assumption is correct. And if they're not correct, then you have to search the entire subtree. But if they are correct, then you kind of like fail, you early exit. So you search down the left subtree, and you find 3 in the leftmost subtree. And now you search the ones to the right of that, and those are 7 and 8. So those produce a cutoff because 7 and 8 is higher than 3. So you think that purple would not let you get to that subtree. And now you do scout search again on the middle subtree, and then you see that you find this first node of each one of those subtrees underneath the middle subtree, and you see that they're all higher than 3. So it turns out that you failed to prove that you can do no better than 3. The main point of the scout search is that you assume that your first move that you searched is the best you can do, and then you do initial passes to verify that assumption. And if you search later subtrees and you find that, for example, in this one, in the middle, and they're all higher than 3, so your assumption is not true. So now you have to do a full search of that entire middle subtree. Is that okay? Are there questions? Okay. So once you find that you have to actually search the middle subtree, you can recursively apply scout search. So you have to search the left subtree in the middle, but now you apply scout search to the middle, like the lower middle and the lower right. And you do a 0 window search there. And you assume that you can, again, you assume that you can do no better than 6, and now you're trying to verify that you can do no better than 6. But you actually can, so you have to search them. And then you apply the same thing again to the rightmost subtree, and you see that you can do better than 6 on the left one, but you do worse than 6 on the right one. And you cut off 2, because the middle subtree already gave you 2. And so you don't have to search that one. So in this example, there were 13 leaves pruned. And the point of scout search is that you can improve pruning a little bit over alpha beta, and that you process most of the game tree with 0 window searches, which reduces, the main point is that it reduces your work because you have to process less. Questions? All right, so now we're going to talk about, so I kind of glossed over how you order the moves. So the ordering determines which order you explore the subtrees in. Alpha, beta search, and principal variation search depend on putting the best moves in the front to trigger an early cutoff. And the main question is, how do we determine which moves are good without doing static evaluation at every level? Like, for example, we only did static evaluation at the leaves, and we call get sortable move list, which is a function in search. And sortable move lists kind of talk about how you populate that later. As I said before, moves are represented in 28 bits, so you can use int32. And to make them sortable, you store a sort key in the upper 32 bits in an int64. And then you sort based on that key. Does that make sense? Okay. So I'll just go over some search optimizations that you can do. That we actually implemented these already, so I'm just going to go through them so it's not super confusing when you look in the code. The most important one is called the transposition table. The main idea in the transposition table is that chess programs often encounter the same positions repeatedly during a search, and you can store those results in a transposition table to avoid unnecessary future searches. And I've listed where you can find those. There's something called Zobrist hashing, which is a technique for hashing a board position, which you use to index the transposition table. And it's a table of random numbers indexed by piece, orientation, and square. So each position has a unique cache. And it produces the hash by XORing all of these random numbers together. And the advantage of Zobrist hashing is that the hash function can be updated incrementally, which is like if you move a piece, you just XOR it out, and then you XOR the new one in. So you don't have to recompute the hash the entire time, or each time. Okay. So the transposition table saves you a lot of work by preventing you from researching things. And there's also something called the killer move table, so the transposition table is like how you determine how to do sorting at things that are not the leaves. And also the killer move table. So the killer move table stores moves that are really good so that the opponent wouldn't let you go down that path, so you don't have to keep recomputing the same values. And the table is indexed by ply because you tend to see the same moves at the same depth. So the killer move table basically just stores moves that triggered a beta cutoff before in your search. There's a best move table, which is stored at the root of the search, and is the move that got the maximum score in your evaluation. And the best move table is indexed by color, piece, square, and orientation. And there's a history table in the code. So these are all basically just things to help you optimize your search and produce early cutoffs. And there's something called null move pruning, which tries to reduce your search space by first not moving and then doing a shallower search to see if this subtree is worth further exploring. The main idea is if you don't move, it basically says like don't move and then do a little bit of evaluation. And if you're still doing really well, even if you didn't move in the subtree, then it's not worth exploring because the opponent would never let you go there because the position is too good. There's futility pruning, which explores moves that only have the potential to increase alpha, and it calculates that possibility by adding a futility margin, which is the most you could possibly gain from going there, and then evaluating a little bit. And if the result does not go higher than alpha, then you skip it, because there's no point in even going that way, because it wouldn't increase your alpha. There's late move reduction, which is after you order the moves at a position, you explore the ones in front are likely to be better, so you explore those in higher depth, and then you explore the ones later with shallower depth, because those are less likely to be good. And some things that you can optimize are implementing a better opening book. I think we have produced a very basic opening book in the handout, But this is something that you can definitely work on and make better because it doesn't have many positions in it right now. And the main point of an opening book is that you store the positions at the beginning of the game that you've already pre-computed, and that saves time in search and can store results to a higher depth. And the KM75 theorem implies it's better to keep separate opening books than to keep the same opening book for both sides. So opening books are really helpful because in the beginning, like there's a huge number of moves that you could possibly make, and searching those takes a lot of time. But if you just if you pre-compute them, you can save them for later. And another useful table you can keep is an endgame database, which is a table for guiding your chess program through the endgame. For endgame positions, the distance from the end might be too far to search entirely, so you can pre-compute them, and then you store who will win and how far you are from the end of the game. And we've given you a C file that you can implement it in. Yeah. Questions? Okay, so I'll just go through some guidelines, some tips for the project. I was giving links at most of the bottom of the slides for where you can read up more on these topics, but there's a chess programming wiki, the link is there, which has many more pages about reading about chess playing programs. Just in general, it's a really good idea to test your code often because it's easy to make a mistake with your optimizations, and it doesn't appear when you search to fix depth. So you can do, if you start up your bot, you can say like search to depth 5, for example, and then you can see it'll tell you like how many nodes per second you searched, and then it'll tell you the best move at the end of that search. But you should test full games using the auto tester and the cloud auto tester and the scrimmage server just to like watch your bot and see to make sure that it doesn't do anything weird. And the testing methodology, I went through some of it. There's a web GUI, there's a Java auto tester, there's a cloud auto tester, and you can do node counts, which is basically just counting the number of nodes in the tree that you searched. And there's function comparison testing, which is if you optimize a function, you should save the old version and then just compare the results.
Let me make a comment about testing. I can't tell you how often in this class we've had student groups who discover that they've made a whole bunch of changes and then there's something wrong with their bot and they can't get back to a stable place when things were correct. They discover the problem, but they've made 30 changes, and now which of those 30 is responsible for the problem? So it's really important to test and have a good test infrastructure for this project. If you have a really good test infrastructure, it's really easy to be innovative in the kinds of optimizations that you do, because then you know that what you're doing is right, and then you can make forward progress. Otherwise, you'll find yourself debugging like crazy and not being able to find the bugs. Some other tips are, this is especially when we get to the parallel part, it's non-deterministic programming. Okay? And the reason is because as you're executing, you're going to be looking up things in a transposition table that you're going to want to share. So that if one branch discovers a value, then another branch can use that. So it's really important to be able to turn that off so that you're, for example, able to search without a transposition table to get all the searching stuff right, and be able to turn that on independently. So that's another really important place to do it. Another thing is that when you do timed searches, okay, the time it takes to do the search will vary, okay, and what you'll end up exploring varies. So as much as possible, you want to do fixed depth searches. In other words, search to 5 ply to test something, okay, rather than searching for a minute or whatever the amount of time is. Because when you start searching for time, that's in fact what you're going to end up doing, but you can't repeat what just happened if you end up searching for that amount of time again, okay? Because the machines are not deterministic, and there may be something else going on that causes, the amount of time to be different. And so for example, if you're making a change that doesn't affect the logic of the program, it's just strictly an optimization, okay? You should get exactly the same result if you do a 5 ply search, for example. Shouldn't shouldn't have changed the 5-ply search. Just the 5-ply search should be faster. And so that's a good way, as much as possible, you want to check things that are deterministic and so forth. And really, as I say, I can't emphasize this enough, how having a good test infrastructure, the ability to control, turn off non-determinism, the ability to test, various parts of this program. This is a pretty big piece of code, okay, for a project of this nature, and you'll feel pretty overwhelmed by it to begin with. Once you settle in, you'll discover it's this wonderful thing where by the end of the project, everybody feels really confident about their ability to handle a decent-sized piece of code. But when you first get into it, it's like, oh my goodness, there's move ordering, and there's static evaluation, and there's the search, and what's going on with that transposition table? Because every one of these things has got cleverness in it. Okay, so it's really hard code to deal with, okay? But you guys are going to do just fine.
So this is the eval.c file in the handout. So this in32 here is the evaluation score, and the main function is called eval, and it takes in a position, and it outputs 2 scores, one for white and one for black. And right now it does, I guess it does material, which counts up the number of pawns. Okay, anyway, so I was talking before about P between and P central, which are your pawn heuristics. And so basically right now it iterates through the entire board. You can see for rank and file are just row and column, and it looks at each square in the iteration, and then it looks at the piece and the color of the piece. And based on the type of the piece, it does some evaluation. So if it's a pawn, it does the pawn heuristics. If it's a king, it does these king heuristics. And otherwise, or both, or not otherwise, I guess. Yeah, in both cases, it'll do, this is an old version, so that's not there anymore, but this is laser coverage, which I talked about earlier, which doesn't depend on what piece it is. This is after you iterate through the entire board. Basically, yeah, and then this isn't here anymore either. But we can look at each of these in depth. So right now, for example, there's P between, which goes through every single pawn in your iteration, and then it'll determine whether or not it's between both kings, and it returns that. So it'll add it to the score if you find that it returns true. And there's P central, which takes in a rank and a file, and basically it increments something, or it gives you a bonus depending on how close you are to the center of the board. So you can look at this. There's a board width, and F is your file, and R is your rank.
She has a slightly
And
I think you have a slightly older version of the code.
potentially.
It's correct on this one.
Is it correct in this one?
Yeah.
Okay. So hopefully this should be, okay. So this is just I guess this is the most updated version. The first one is P central. So this just counts the difference between where you are and the center of the board. And it gives you some bonus depending on how far you are from the center. And this one is between, so this is between, which is a helper for P between. And it tells you whether or not your pawn is in the bounding box determined by the kings. And this one is K face, which is given a king, you look at its orientation, and then you give it a bonus depending on which way you're facing and how far you are from the center, I think. No, how far you are from the opponent. So F and R are where you are, and now it does the delta between you and the opposing king. And then you do some scaling depending on which direction you're facing. So this is just your orientation. And then this is K aggressive, which gives you a bonus for how far you are from the edge of the board. So you can see here, Op square is where the opposing king is, and delta file and delta rank are how far you are from the opposing king. And then you add the bonus depending on like which case the deltas fall into. And this gives you a bonus if you're farther from the edge of the board. Yeah, and I guess this one, so mark laser path, or not mark laser path, there's L coverage, which is the most complicated one, probably. And basically what laser coverage does is that if you, basically it like takes a position, and depending on what side you are, it generates all the moves that you could possibly make from that position. So, see, you generate all with color, which means that given your color, you generate all the possible moves that you can make, and you get a list of moves, and you iterate through it, and then you make each of them, and you draw a laser path, and what the laser path does is basically it bounces off some pawns. And for each square, you increment the distance basically along the path. And if it takes the minimum distance over all these possible paths for each square, and if it doesn't touch a square, then it's just 0. And it divides it. Well, I can go into this. Yeah, so it draws the path through this while true loop, and then it adds, or this is just changing the orientation if you need to like bounce off a pawn. But this one is setting you keep a laser map, and you keep the minimum path of a laser that would possibly touch that. And no, this is just changing the orientation. But yeah, so then you generate this map for all the possible moves that you could do, and then you do some scaling. So depending on the distance from the opposing king, you iterate through the entire board, and you divide the minimum distance by the actual distance from the laser. So the maximum that this ratio can be is 1, and then you multiply it by 1 over the distance. Yeah, so this one is really complicated, and there's a lot to optimize here. For example, you probably don't have to iterate through the entire board each time. Because like even in eval, like here, you have to iterate through the entire board to find each piece. And if you stored a better representation, you might not have to do that. Like if you just kept track of where the pawns were. Because you already keep track of the kings separately. So that's one thing you can do. Yeah.
There are two basic strategies for changing the representation of the board, and maybe there are more, but the two basic ones are you can, instead of keeping the whole board with a piece on each square and then having to go and search for where the pieces are, you can keep just a list of where the pawns are and what the locations of the kings are, so that when you want to make a move, you can just go through where they are rather than having to search through all 64 squares of the board. And then the other strategy that you can do is use what's called bit boards, where you have a 64-bit word for which if there's a pawn in a given position, you set that bit. And so there are different ways of representing things that could possibly definitely be more efficient, but you have some choices there. And there's also, one of the complexities of this is that to change the representation, there's going to be places in the code, you need to find out where they're assuming, that things are. So, you say, oh, I'll change the board representation. Oh, I didn't realize that over here there's another place that it's using the board representation, and so forth. A good strategy for changing board representation is to actually keep both representations around, okay, while you migrate functionality from the old one to the new one, okay? And then the advantage of that is that you can actually, then use assertions to say, the old one and the new one are the same, Okay, so implementing conversion functions is really good. That's, you know, being able to take, for example, if you decide you're going to use a bitboard representation, have a function that converts the bitboard to the standard board, so that then you can compare whether you've got the same thing. Okay, and you know, eventually you'll want to get rid of that, but to begin with, you know, and of course that'll slow you down because you're doing more things, but it'll allow you to get it correct with a new representation. And once you've got it correct with a new representation with the old one gone, that's when you have a chance to make things go fast. Okay, but it kind of is taking 2 steps backwards, you know, to take 5 steps forward. I say not 1 step and 2 steps, but, you know, because really, you know, often, you know, you really are slowing things down, you know, considerably in order to, you know, convert from one representation to another. The most important thing is that you maintain the invariant of correctness in your code. Okay, you do not want to make something that goes faster but is wrong and have to debug the correctness. You'd much rather ensure that things are correct, okay, are moving to the place that you want to do it, and then you can optimize for performance. Okay, so the most important thing is keep that invariant of correctness. And that's where the testing and so forth comes in, having good test infrastructure and having assertions littered throughout your code.
And then we can go through the move generation. Oh, actually, okay, so just as an example of how you would possibly, one way of determining whether or not you stayed correct. So this is an example of a place where I compiled the code. See, the binary is called LiseRHS. And if you look at help, it gives you some options for what you can do. For example, there's display, and that's the opening position. And let's say I want to search. So I do a fixed depth. I do go depth 3. And it tells me the number of nodes that I searched at each depth. And so if you make changes, if they're non-determined, or if they're deterministic, these node counts should stay the same. So that's one way of telling. So you should keep track of this and make sure that they're the same. And also you can do perf_t, which gives you the number of possible moves you can make. And that should be the same no matter what you do. So that's one way of testing. There's other ways, but yeah. So if you go to like higher depth, you'll get more node counts. Yeah, and here this is, the way you're reading this is nodes that you searched at this depth, and this is nodes per second. So you want to make this one faster. Okay. Yeah, so that's how you run the code. And, oh, I was supposed to do a demo for the auto tester, okay. So let's say I wanted to do, to do that thing. So when I made it, it's in a binary called LiseRHS, and then you do Liser. And then here you can type in commands. So if I do so you basically just type in commands from this, like you run your binary. For example, you do perf_t.
This is the UCI interface that we talked about, okay? And in LiseRHS.c is the implementation of that. And so if you want to add your commands to it to help debug, you can enter, if we go into LiseRHS.c, you can see the table.
That's the help.
What I want to do is show the table of all the options, which is...
There's a table of all the options.
There we go, okay.
This is just the heuristics.
So these are tables of heuristics and so forth, which allow you to set the values of the various things. There's actually and to say, you know, how much is this heuristic worth to the static evaluation? Okay, and so you can, and through these, all of these can be set. So you don't have to recompile the binary if you want to try out things with different, if you want to auto test with, you know, let me count this as worth 1/3 of a pawn, let me count this as worth, you know, half a pawn, or whatever, you can just enter it through the UCI interface, and in the auto tester you can specify that, so it'll just test those without you having to recompile binaries for every one of them. Okay, and so there's a table here which basically says what's the name of the heuristic, what's the variable that is going to be set, what the default value is, and pawn EV value is the value of a pawn. Okay, and if there's any restrictions on the range of those values, what's the smallest it can be, what's the largest it can be. Okay, so you can edit this table and so forth, and as I say, you can set it through the UCI interface. So it's really a very flexible way of getting access to anything that you want to do. You can put your own commands in there, okay, including new heuristics or whatever. And there's some things in there, for example, if we go to the other part of where they actually are parsing the UCI stuff, you can, so it basically takes it, it parses it, figures out what the command is, and then implements the command. So all that kind of stuff you have control over, okay? So that will help you in, choosing to do other things. So, for example, if you search for perf-t or something in there, right? So if you have perf-t, here's what the correct output should be, and now here's the code that it executes. And perf-t is in a different file. I think it's in the move generation file.
Had the wrong output?
That may be for the older game. Yeah, I actually noticed a couple of other bugs in there that hadn't been fixed. So we will make sure that those are. Basically, it's just dead code is what's in there. We need to clean up some of the dead code. Some of the code is from last year, and we changed the game, and not all the dead code got eliminated.
Yeah, it'll be fixed for when I make the repos.
Yeah. So we're just finishing up some. Right now, I think it's all cleanliness. But if you find any bugs like that, let us know. We'll fix them and so forth. Appreciate that. If you do see other inconsistencies or what have you. Good. So great project. This is like lots of fun. The next month is going to be lots of fun for all of you. You may not think it's fun every minute of the day, but you'll have a good time. It is fun.